Hello. Now, as we are finished with device packages and with module packages, we have to mount these on some carrier, and to that purpose we will look at substrates. So one of the most important substrates we can have is the printed wiring board, as we can see it here. It can be produced in a low-cost version and also in a high-density version, as we see it here from an aerospace application. On the other hand, there are also other substrates. For instance, these here are ceramic-based substrates, thin film and thick film hybrid substrates. And today we will see about topology of such substrates and also about technologies of these. What is important in a substrate? Of course, we must be able to mount our devices, and these devices can be mounted closer together or with a larger distance in between. On the other hand, the substrate itself, it must provide conductor lines, as we can see them here. And a typical substrate has several active layers of copper. And so in that case, here we only see 2 layers which are active. There is a third one on the back side. And it is necessary to come from one side of the substrate to the other to have a connection, and that is accomplished by so-called via holes. And in printed wiring boards, these are also called plated through holes, PTH. So we can see there is copper going through this plate. And now there are several features which are important. These via holes have certain distances. Often these distances are quite regular, and so we call this regular distance the grid of the via holes. On the other hand, we have conductors, and these conductors have a line width, as we can see it here. And we also have a certain clearance from line to line, and both the line width plus the spacing is something like a unit which can be repeated from, let's say, from bit to bit, for instance, and in that way we can also define a regular structure, and that regular structure is defined by the pitch. The pitch has the sign PC, and this pitch is just the sum of the width plus the spacing. Okay, that's very important. You can imagine, let's say, boards which have a large pitch, wide conductors, wide clearances, and on the other hand we can have so-called fine pitch boards. Another property which is important is the number of layers. Here in our lecture we denominate this as capital letter S. Okay, so we can see we have the grid, we have the line spacing, we have the line widths, both make up the pitch, and that's what we can see on a typical board. On the other hand, when we make a design, we have a certain wiring demand. So imagine you take a board, place in your computer the components, interconnect all pins which have to be connected according to the schematic, And in that way, we have a certain wiring demand which you get out from your layout program. On the other hand, you cannot use a printed wiring board which just fulfills that wiring demand. In fact, you have to use a printed wiring board which can fulfill a much higher wiring demand. The reason is that in a real board we have via holes, conductor lines go around corners, and in that way we can say what is required from the board is this demand divided by the efficiency of the technology, and so typically it's twice the wiring demand which must be provided by the board. Please note, the wiring demand is just measured in meters, so you need a certain length of connections. Okay. When we regard a certain piece of printed wiring board, and we could say we regard a certain area which is a p², and on that p² we need a certain conductor path length. And the so-called connectivity is a property which gives us the length per area. So it is a property of a technology. And we can show that this connectivity, which is the possible length of conductors per area, p², is just the inverse of the pitch. We can easily make a construction where we have here the p² area, and on that area we have certain conductor lines, and in that way we can compute, or we can prove that we have a certain number n here, and you could say n times p is just the conductor length, and if you use that, you can say you can put it in here, and in that way you end up with this relation. So you could say the pitch is a length. You have the inverse of a length, so 1 per meter or 1 per millimeter, and it's the same like length per area. And in that way, we can see that we can get the connectivity, which again is a theoretical value, because again, we can only use maybe 50% or so of that connectivity. Now it's important, the total connectivity of a board is S times C. So that means the total connectivity of a multi-layer is just the number of layers divided by the pitch. And the total connectivity is a characteristic property of a printed wiring board, in the same way as the pitch also is a representative of a certain technology. So you can have high-tech boards which have a small pitch and a high conductivity, or you can have low-tech boards which have large pitch, maybe only a millimeter or so, and also have a low connectivity. So generally, when we look again at a board as a component, we have a wiring capacity on that board, and that wiring capacity is the square of the area times the number of layers divided by the pitch. And that is the theoretically possible pad length on a substrate with the area p square and with the number of signal layers S at a pitch of Pc. So when we look at pitches generally in assembly and packaging, we can say there is a very wide range. So we can have even conductor lines on chip, for instance, or on silicon, which are in the sub-micrometer range. And on the other hand, pitches can go up to, let's say, centimeters. So that means we have maybe 4 or 5 orders of magnitude of pitch we can have on some wiring structures. Normally, when we make a design, we must select an appropriate substrate technology. And normally, nowadays, that information we have is given by the layout program. But on the other hand, it's sometimes convenient to have some rule of thumb in order to estimate, for instance, the required track length. For instance, if we have a component, so a processor or so, with a number of IOs, which is NT, and we put it on an area of edge length P, so here would be the device. You can say the required track length per component is something like twice the number of IOs multiplied with the area and multiplied with some efficiency factor, which is somewhere between 0.5 and 0.9. And in that way, we can also compute the required wiring density of one layer. And again, that wiring density is the number, that's the total track length per component divided by the area, divided by the number of layers. And in that way, we can say the required wiring density is something like twice the number of IOs times this efficiency times divided by the edge length P and divided by the number of layers we put. Of course, for instance, if the number of layers is higher, the required wiring density of one layer is lower. It makes no sense selecting 32 layers or so. It is reasonable to keep this in a not too high range, and so we can play around with numbers of layers, let's say like 2, 3, 4, 5, and so on. And in that way, we can estimate it. And here we can say, for instance, if we have a if we have a larger area, 200 IOs, 4 layers, we need typically 75 centimeter per square centimeter, and on one layer we just need 19 centimeter of conductor length per square centimeter. So you can imagine that is already a quite long conductor length per area. So in that way, we can estimate, do we need fine boards, do we need coarser structures on the board, and how many layers is reasonable here. If you look at packages, we also define the packaging efficiency. The packaging efficiency is the active silicon area per active substrate area. And in that way, of course, we typically have efficiencies below 100%, because typically the chip is smaller than the substrate. So we have already treated multi-layer substrates, and what are the reasons we have these? It's first of all the limited total area of the board. So sometimes we do not want large area boards, but well confined areas. Just imagine a USB stick. It should not be 5 centimeters long, but we want it maybe only 2 or 3 centimeters. Also, we can decrease the required wiring density per area on one layer. So that means maybe no fine pitch, coarser pitch, but more layers. And it can just be topological reasons. So for bridging, for instance, and some interconnections on board, it is sometimes necessary to select a minimum number of layers. And for instance, sometimes we need 4 layers, and with less layers we cannot accomplish wiring on such a board. Now, in this lecture, we will treat several classes of material. Of course, we cannot have an all-metal wiring board, but we can have polymer substrates, and these are called printed wiring boards or printed circuit boards. It's just synonymous, and we can use both terms. We can also have flexible circuits. Flexible circuits are a foil, let's say, of polyamide with copper. Printed wiring boards are rigid structures, typically made of epoxy glass and copper. And on the other hand, we can also have ceramic substrates. Here we have so-called thick film technology. We have so-called LTCC technology. That's a multi-layer technology like we had it in packages. And we have direct copper bonded ceramic substrates, which are more for power applications. And then we have miscellaneous substrates, which is typically thin film substrates. These are using silicon or ceramic carriers. Sometimes we even use polymer carriers. And thin film means we have only extremely thin layers of metal in the micrometer range. Yeah. Now let's have a look at history of wiring and substrates. Here is an example I found on the internet. That's a way like radios and other equipment were wired maybe before the year 1950. That was created by someone just for fun, but it is some kind of, let's say, air wiring. just soldered together. We can also solder in a socket and plug in, for instance, a small microcontroller. We can solder on a quartz, capacitors, and so on. That's the very old-fashioned style, let's say before year 1950. Of course, you can imagine to produce such a thing it's all handwork, so it's not efficient. On the other hand, maybe some of you still have seen such so-called through-hole technology. It's a through-hole assembly, and we can see here we have the printed wiring board. It's similar to what already exists. The components all have pins. These pins are bent in a way we can plug these pins into holes in the printed wiring board, and then we solder these. So all of these here are soldered joints. Okay, and that technology was used at least, let's say, on a large scale until 1990 or so. Later on, it was still used in some applications, but after that we had another technology, which is so-called surface mount technology. But between surface mount technology and through-hole technology, the boards didn't change very much. And now in the following, I would like to explain a little how such boards are created. Here, that is a board for SMD. That is something which is very modern. For instance, here we have an infrared sensor which can measure the oxygen saturation in the blood just by infrared absorption. What we can see here is the inside part of that board. So we can say we have the center part and we have two sides of this board which are positioned along that part of the housing. This board is, so you see the front side and the back side, this board is cut out from this larger plate. But this plate has several functions. One of the functions is that there are several structures which are later on independent electronic units. They are all connected. So we do not process a single circuit, but we can process many circuits. First of all, in the production of such boards, that's efficient to have larger areas with many, so we can increase production speed. And also when we later on process such boards, the pick and place operation is much more efficient because we can have, here in that case, just 4 substrates on, or 4 printed wiring boards in one substrate on one machine. In that way, we can also have some auxiliary structure which has test points here. So in the end, we can test the devices, we can calibrate them, and if, for instance, they are out of range, if they don't work, we just don't cut them out. Yeah? So they can be lasered out, for instance, or we can use a machining operation. And in that way, we have a very efficient process. And as we can see here, it's all surface-mounted devices we have on this printed wiring board. Okay, but now let's go back to the development. And here we can say in the beginning, that was around 1950, the invention was to have one plate of such polymer material and to have just copper structures. So that is copper, and that often was paper with phenolic resin. That was a very cheap material we sometimes still find, for instance, in electronics for washing machines or so, which must be extremely low cost. On the other hand, we found that often it is not sufficient to have only one layer, so people invented the two-layer structure. In the beginning, we just had something like this. A hole was drilled. We have here the copper. A pin was put in. It was soldered. And in that way, we could create a through-hole interconnection. Again, that is not very efficient. And so another process was developed where we have already a through-hole metallization in our plate. And we have already seen this term plated through hole, and that's just such an element here. What we will see in more detail is how this was produced. The next thing was not only to have one layer with plated through hole, but to have multi-layers. For instance, in our case here we see 4 active layers, like 2 signal layers, 2 power layers, and we have a plated through hole through all of that board. This multi-layer was developed more and more. We had more and more layers. For instance, here we have 6 layer. And okay, there are several variations. What is also important, sometimes we need some intermediate interconnections between these layers we have. So here, how many would it be? 2, 4, yeah. Okay. Now, what is the process? In order to get to such boards, and here a very important invention was made. We have this FR4 material, which is typically epoxy glass, and that material is covered with a copper foil. So you could say this copper foil is more or less glued onto this epoxy glass, and this copper foil is drilled. So we have here a hole. So typically the hole is somewhere in the millimeter range in the initial technology. And okay, how can we metallize it? In this invention, the whole board was put into a certain chemical bath, and that bath has some catalyzing action. And that action, that catalyzing action leads